Hello, everyone. I'm Sandra, a postdoctoral research associate at Imperial College London. Today, I'm going to present our work guarantee, which is a framework to have private and attestable machine learning on end devices with ARM's confidential computing architecture. This work is done in collaboration with Sina, Mohammed, Marius, and Hamid, who are also at Imperial College London. Nowadays, we are seeing an increasing number of machine learning models deployed on end devices such as mobile phones, gateway routers, or IoT devices. On-device machine learning, or ML, can have several benefits, such as avoiding the need for sending user data to the cloud, latency reductions, and facilitating functionality such as private personalization. At the same time, on-device ML also comes with challenges. From the point of view of the model provider, that is, the entity that trains and supplies the model that's run on the end device, there are two desirable properties. First, providers want model privacy. That is, they want to ensure that their proprietary information, such as model weights, are not exposed to external entities. Second, providers want model verifiability. That is, they want to ensure that their model is running as expected and has not been tampered with. We look towards ARM's confidential computing architecture, or CCA, for model protection. CCA allows for the creation of dynamic, hardware-protected confidential VMs called realms. CCA's various advantages that I've laid out on the slide make it a promising choice for our scenario. Due to widespread deployment of ARM's trust zone, we also envision that CCA will be available on end devices in the future. We thus develop guarantee that uses CCA for end devices to run ML models within a realm in a private and verifiable manner. Our system consists of three entities. There is a model provider that wants to deploy a model for inference on an end device which supports CCA. The figure shows a simplified view of CCA on the client with the realm world and the untrusted normal world. There is a third entity called a trusted verifier. The client first obtains a realm image from the verifier, which can be used to create a realm VM. A shared folder is also created between the realm VM and the normal world. Once the VM is initialized, it establishes a connection with the model provider. It sends an attestation report to the provider, which contains information on the state of the realm. The attestation report is a feature supported by CCA. Once the provider verifies the report and is certain that the realm is running as expected, it sends the model to the realm. The realm signals to the normal world that the model is ready for operation. The realm and the normal world communicate via the shared folder. The normal world places its inputs to the model in the folder. The realm reads the inputs, feeds it into the model, obtains the output, and places this in the folder. We create an implementation of this scenario. As ARM CCA is still currently under development and there is no CCA-compatible board available, we use the Fixed Virtual Platform, or the FVP, which is a simulator. The FVP has a CCA integration with the components necessary to create and run realms. We implement a test scenario with a small 16-megabyte TensorFlow-Lite image recognition model. There are applications running in the normal world and the realm to feed input to the model and to write the output from the model in the shared folder. We perform a preliminary evaluation to understand the overhead produced by a realm VM over a normal world VM. The FVP is not cycle accurate, making timing measurements not representative of what they would be on an actual board. Thus, we measure the number of instructions using FVP's model trace interface. We measure the instructions during each step of the ML process. Our preliminary results indicate that for the model inference, the overhead of the realm is 1.17 times the normal world, making this a promising option to run ML models. Most overhead that we observe comes from I/O operations. We note that our implementation does not have any optimizations to reduce this overhead, and we will look into alternative designs next. We are currently working on a larger scale measurement study to understand the impact of running larger and different types of models within the realm. We are also investigating other aspects of the deployment lifecycle, such as model updates and the changes in the trust assumptions that we have made. There are many other considerations when deploying ML on end devices, which we have not considered in our preliminary evaluation and may necessitate changes to CCA or the interactions with it. These include attacks to the data pipeline, running models from multiple providers on the same device, and policy enforcement to ensure that the client and the model provider behave in accordance with the agreement they have. With that, I'd like to conclude and also point to our paper and code repository. We have released code and a setup guide on FEP to facilitate further research in this space. Thank you.